Alright guys, we're going to go through 5.2 now. Hopefully you just finished the video covering 5.1 stuff. So 5.1 was dealing with exponentials and the natural base of e. 5.2 we're going to be talking about something very new called logarithms. So logarithms is a new concept, it's a new function, it's a new operation that you guys have not come across yet before in any algebra class, or you shouldn't have any. Should be the first time. So a logarithm, we talked in chapter 4 about inverses. So inverses, like inverse functions, well, we talked about inverse functions, where x and y coordinates of functions are switched. So square root functions are the inverse of squared functions. Cube root functions are the inverse of cubed functions. So exponentials also have inverses. So if you have something like 2 raised to the x power, this is called an exponential function where it always doubles. It's always doubling forever and ever. It's a function that grows very quickly. But this function does have an inverse, just like x squared. So x squared and the square root of x. So these functions are inverses of each other where their y values and x values are switched. 2 to the x is also going to have a function that will have x and y values switched, and that's what we call logarithms. So logarithms are the inverses of exponentials. They're inverse operations as well, not just inverse functions. They're inverse operations. So first of all, let's just deal with the general format of what a logarithm looks like. So logarithms, because they're inverses of exponentials, there's a quick and easy way to kind of convert those or switch into different forms. So we have 4 to the third equals 64. And it's asking us to rewrite as a logarithmic equation. So this is an exponential equation. And if you see below, this is what a logarithm looks like. This is a logarithm. And for these questions, it's asking us to rewrite these expressions in their, basically in their inverse form. So we can do that. So if you have an exponential, we're going to say what's the letters that they typically use? We're going to say b for base. So if you have a base and it's raised to some sort of m power, that's going to be equal to some n number. Okay, so if this is the case right here, I'm going to draw a double-sided arrow. A logarithm with base b of some variable n will be equal to m. Logarithms always equal exponents. Logs equal exponents. So you can see here, this is an exponential model. This is an exponential equation. Exponential equation right here. This over here is a logarithmic equation. Logarithmic equation. So exponential and logarithmic. Whenever you write the logs form, so notice that the m is the exponent whenever it's in exponential mode, but the m is what the logarithm should equal. So the log will equal whatever the exponent is in the exponential equation. So we're going to go back and forth between these forms depending on what we have. So here we have an exponential model, but it wants us to rewrite it as a logarithmic equation. So what would this look like? So you should see your answer should look like this right here. So for A, you should have a logarithm. You need to give it a base number. So this is called the base of a logarithm. So logarithms always have base. You should always, I guess not always, I'll tell you when, but most of the time you should give a logarithm a base number. So there's a base number, and this is not multiplication. So this isn't saying log with a base multiplied by n. This is a argument. It's a value that must be provided for the logarithm. It's called the argument. So in a logarithm, you should always have a base number, a base, and an argument, and that will give you the value of the exponent. So what's going to be the exponent here? You can even start with this right here, because we can just look at this exponential and look at the exponent, and so I can tell you right here that this is going to be 3 right here, because logarithms always equal exponents. Now, exponentials also have a base, right? So this is the base of the exponent, and here we have the exponent, and this is its value. Okay, so notice that the base of the exponential will also be the base of the logarithm. They will always be the same. So the base of our exponent is 4, so the base of our logarithm will also be 4. So this will be 4. And then this, what the value of the what the exponential equals is what's going to be the argument for your logarithm. So this will be 64. So log base 4 of 64 will equal 3. And then for this next one, we're going to do the same thing, but this is given in a logarithmic form, logarithmic equation. It wants us to write it as an exponential equation. So what are some things that we can remember? Well, logarithms equal exponents. So that tells me that this has to be 0 right here. Okay. Also, the bases have to be the same. So this logarithm has a base of 6. So my exponential has to be base 6. And the argument of the logarithm should be what the exponential equals, so 1. And it should make sense. 6 to the 0 power is equal to 1, which is what we know. Anything to the 0 power is equal to 1. Okay. We have a couple more. We have another example right here. So again, we have an exponential. Let's write it as a logarithm. So notice that the base is 2, so the base of my logarithm is going to be equal to 2. I also know that logarithms always equal exponents, so the exponent here is 5, so that should be 5, and then that means that this has to be 32. So log base 2 of 32 is equal to 5. Okay, for part B, we have have this logarithm, but it wants us to write it as an exponential with a base, an exponent, and a value that it equals. So remember that the base of the logarithm, if I'm rewriting it as an exponential, will also be the base of the exponential, so base 5. Okay, logarithms also equal exponents, so -1 has to be the exponent. And then that means 1/5 has to be the outcome right there, which is also true. We know that negative exponents means reciprocal. So 5 to the -1 is 1/5, because that's the reciprocal to 5. I think we got one more right here that you guys can practice. So we have a logarithm. We're going to write it as an exponential. So I see that the base of the logarithm is 3, so the base of the exponential will be 3. Logarithms equal exponents. So if this equals 4, that means the exponent has to be 4, and 81 has to be the value, and that's true. 3 to the 4th power is 81. All right, for this one right here, we have an exponential model. We want to rewrite it as a logarithm. I see that the base of the exponential is 8, so the base of my logarithm is 8. I know that logarithms must equal exponents, so the exponent here is -1, so that has to be -1, which means that the argument here has to be 1/8. Okay, all right, so that's your introduction to what logarithms are. Logarithms are inverses of exponentials. So yeah, there you go. Probably doing something very similar here. So for these questions right here, rewrite each equation as requested. So rewrite as a logarithmic equation. So yeah, it is the same. So here we have base e of x equal to 4. So what will this look like a logarithm? So for a logarithm, you have a log. You're going to have some sort of base number. You're going to have some sort of argument, and that's going to be equal to some sort of number, right? So keep that in mind. That's what your answer should look like. That's how we should type an answer. So log. Now I'm gonna write something, but it's not going to be our answer. So I see that the base is e, so that means the logarithm has to have a base of e. Okay. Remember that logarithms equal exponents. I can see that the exponent is x, so this logarithm has to equal x, which means that the argument has to be 4. So log base e of 4 should equal x. But this is incorrect. Well, it's not incorrect, but that's not how we write this right here. So e is a special number. Special number, that means its inverse has a special logarithm. So e is the natural base. And so whenever we write its log, whenever we have a log base e, you don't ever write something with a log base e. Instead, because e is such a special number, its inverse, its logarithm, has a special notation, and we call it a natural logarithm. So this is called the natural logarithm, the natural log. And the notation for the natural log is ln. I know that sounds backwards. Natural log ln. It's not an in either. It's called ln. I guess you can also write it like this, ln. But basically, I think it's I think that originates from a French word, like log natural or something like that, if I remember correctly, which is why it's called ln, so log natural rather than natural log, then nl. I guess that kind of just stuck. So ln refers to the natural log. And so where I said, whenever we write logarithms, and I said logarithms always have a base, that's true, but there are actually two specific logarithms that we don't write the base. There is a base, but we don't write it whenever we use it. So for here, for example, instead of using log base e of 4, that should be rewritten as natural log of 4. So whenever I see this expression, yes, it does mean log base e of 4, but in math we don't write it as log base e. We have its own special expression for a base of e. We call it natural log, and we don't even write the e. The e is just automatically known that that's what its base is. So whenever you see ln, we know that it is a logarithm of base e. We just don't specify that, we don't write it out explicitly. So we should say natural log of 4 is equal to x instead of using this notation right here. Okay, so keep that in mind. So natural log is a logarithm of base e. Log of base e. All right, so for part B, you can see we have another natural logarithm. It wants us to write it as an exponential equation. So we have natural log of 9. So whenever I write the exponential, its base has to be e because that's the base of the natural log. So e, now what's going to be the exponent? Remember that natural logs or logarithms always equal the exponent. So this is the exponent. So y is the exponent, and that must mean that this must equal 9. So there is your answer for this one, and that was the answer for part A. I think 11 will be very similar, so rewrite each equation as requested. So we have natural log of 2 is equal to y, write as an exponential. Well, because this is a natural log, the exponential will have a base of e, y will be the exponent, and it will equal 2. E to the 7 is equal to x, so and we want to write this as a logarithm, we're going to have to use natural log notation because we have a base of e. I know that logarithms always equal exponents, so this must equal 7, and that means x has to be my argument. All right, for 12, looks like it's the same thing. We have a natural log, so that means whenever I write it as an exponential equation, we have to use the base of e. Natural logs always equal exponents, so my exponent has to be 3, and that is going to have to be equal to x. For part B, we have an exponential expression. We want to write it as a logarithm, so we have to use natural log notation. And then logarithms always equal exponents. The exponent here is 5, which means y has to be the argument. All right. Now we're going to evaluate logarithms. So for evaluating logarithms, log base 6 of 1 over 6 right here. So how am I going to evaluate this logarithm? By hand, not with a calculator. So an easy way to do that is if you know exponentials are actually really helpful for this. This is why we just learned what we did. It's actually very helpful to convert between them because sometimes it's easier to see the value when you convert. So for example, you see log base 6 of 1 over 6 and you think, what does that equal? You think, I have no idea, right? Because I am in the same boat. I have no idea. But I'm much better viewing exponential equations. I'm way better with exponentials. So I'm going to write this expression right here and this expression as an exponential. So I see that it has a base of 6. So then my exponential equation should also have a base of 6. Now, logarithms always equal exponents. So this logarithm should give me the exponent to this 6 right here, but we don't know what this is. That's exactly what we're trying to solve for. So this is like kind of unknown. The exponent is the unknown part right here. But I do know that this must equal 1 over 6 right there. So I've rewritten it as an exponential, and actually now it should be a little bit more clear as to what the power of this exponent should be, as long as we've been paying attention in class, especially in the last unit with our properties of exponents. If I have the 6, if I have a number of 6, what power do I need to give it to get 1 6 right here? So if you remember how exponents work, 6 to the 0 power is equal to 1. Anything to the 0 power is equal to 1. 6 to the first power is equal to 6. 6 squared is equal to 36, so on and so forth. Okay, so you can see we multiply by 6, we multiply by 6, and then if I want to keep going, find 6 to the third, I'd multiply by 6. Now this isn't showing anything as 1 6. But what if I go backwards? So whenever I use this rule in the reverse direction, let's say I divide by 6 and divide by 6. So dividing by 6 right here, 36 divided by 6 is 6. Yep. 6 divided by 6 is 1. Yep. Okay, well then what if I want to find 6 to the negative 1? Well, I take 1 and I divide it by 6. Oh, there we go. So how do I take 6 to what power do I get 1 6? Negative 1. So that tells me that this value of this exponent must equal negative 1. So hopefully that makes sense, but that's the way I think about it. I'll do something similar here. So I have a base 4. So 4 to what power? Because I don't know. Logarithms equal exponents. So 4 to what exponent? 4 because that's the base. But 4 to what power will give me 64? All right, well, I know 4 to the first power is 4. I know 4 squared is equal to 16. 4 to the third is going to be equal to 64. There you go. So I have to use 4 to the third to get 64. Excuse me. So that must be the value of this logarithm right here. All right, and we got a couple more right here. So I see that the base of this logarithm is 8, and logarithms equal the exponents. So 8 to what power is going to give me 1 over 64? All right, well, let's use 8. So 8 to the first power is going to be equal to 8. Well, notice that this is a fraction right here. Okay, well, then I have to I don't want to go upwards. I don't want to increase the power. I want to decrease the power. So 8 to the 0 power, that's going to be 1. 8 to the negative 1, I'd have to divide by 8. Okay, what about 8 to the negative 2? Well, that means I have to divide by 8 again, which means I'm stacking the powers in the denominator. So it's going to be 1 over 8 squared. Well, 1 over 8 squared is equal to 64. So this is 1 over 64. All right, perfect. I found my value. This has to be equal to negative 2. All right, I got 3 to log base 3 of 27. So let's say I do 3 to some power must equal 27. Let's write out some powers. So I know that my power has to be increasing. I know 3 to the first power is 3. I know that 3 squared is equal to 9. And 3 to the third is equal to 27. There we go. So this has to be equal to 3, the exponent right there. All right, these are actually should be the last couple questions. So for question 15, evaluate each expression. Reminder, when a logarithm is written as a log without an explicit base, it refers to the common logarithm. So this is the other logarithm before. So I said that we always write logarithms with a base. Every time you write a logarithm, it should have a base, except for in two cases. The first case is in the case of natural logarithms, because its base is e, and we don't explicitly write it out as e. The other case where we don't write the base is with a common logarithm. So a common logarithm is whenever the base is 10. So common logarithm has a base of 10. So log base 10. How should I write this? It has its own special notation for a log base 10, and that is just to write log. So whenever you see a logarithm and the base is not explicitly written out, it means that its base is 10. Okay, so for part B, you can see that here. Look right here. Oh, this logarithm doesn't specify its base. Doesn't mean it doesn't have one. It just means that that's the common logarithm. Its base is 10. If it makes you feel better, you can write that in there if you want, but you're not going to see people write that in there because that's just the way the notation goes. Okay, so evaluate each logarithm. So we have a log base 5 of 5. Okay, so this is a property. So we can use the same property as we did before, where I can say 5 to some power must equal 5. Well, that means that this has to be equal to 1. 5 to the first power is 1. So here's a property. A logarithm with a base of, let's say, base of m will always equal 1. So if the value of the base is the same as the value of the argument, the logarithm will always equal 1. So this is equal to 1 because we're doing a log base 5 of 5. Okay, now for this one right here, this is a log base 10 of 1 over 10. You can think about this in a couple different ways. The long way to think about this is to evaluate it the same way we've been doing. So 10 raised to some power is equal to 1 over 100. All right, well, it is a fraction, so that means we have to say, so 10 to the first is 10, but I'd have to decrease the power if I want a fraction. So 10 to the 0 power is 1. 10 to the negative 1 will be 1 over 10. 10 to the negative 2 will be 1 over 10 squared, which will be equal to 1 over 100. So there I can see that this value has to be equal to negative 2. Another way we could have done it, though, so that's one way that always works. So if you think about 1 over 100 and seeing that the base is 10, so I know that it depends on how good you are with your exponents. So I could tell you right now from the beginning, I know that 1 over 100 is 1 over 10 squared. And I know that that's equal to 10 to the negative 2. So I could rewrite my logarithm as a log of 10 to the negative 2. And again, this is a common logarithm, so it has a base 10. And I can use the same property that I used right here. Log base 10 of negative 2. If the log base is the same as the argument, that must equal 1. In a sense, they just cancel each other out. Log base 5 of 5, they cancel not to 0, but to 1. And that's what we mean by cancel. So log base 10 of 10, well, that just cancels to be 1. I'm going to be left with negative 2. So that's one way you can also look at it, is try to match up the bases of these numbers right here. All right, for 16, using a calculator. So that should be pretty straightforward. So natural log, you can use a Desmos calculator, or you can use whatever calculator that you have. And it's pretty simple. You're just going to type in ln. So whenever you type in ln, it should give you the function that you need. So natural log, and then you can just type in the number. So for us, it was 33.7. So natural log of 33.7 becomes 3.517. So 3.517. Then you have a log of 3 over 7. So you can do the same thing if you're in Desmos. You can just do log, or if you have a calculator, there's a button on calculators that says log. There's also a separate button for natural log, so watch out for that. If you have your own calculator, there's a button for a log, and then there's a button for a natural log. Okay, so log of 3 divided by, whoops, I want to make sure that I put parentheses here. 3 divided by 7, and there I get negative 0.36, 8. Thank goodness that rounded up. Am I right, guys? Negative 0.36h. We wouldn't want that number that you guys always talk about these days. Okay, and you can do the same thing for question 17 on your homework, but in any case, I'm probably going to wrap that up and call it good. So, welcome to logarithms.